Hey everyone, and welcome back to the Deep Dive. Don't forget to hit that like button, subscribe to the channel, and ding that notification bell so you don't miss out on future explorations. Today we're diving deep into the world of stars. Well, their whole life cycle actually. From their dazzling beginnings to their, well, kind of bizarre endings.
Yeah, it's a pretty wild ride from what I've read.
It is, and whether you're a UPSC aspirant gearing up for GS1 geography, or a student just fascinated by space, or heck, even if you just enjoy stargazing, this deep dive is for you.
Absolutely. And what's really fascinating is that a star's life isn't just about the star itself, you know? It's about the forces that shape the entire universe.
Right.
It's about the elements that make up everything around us. And
Mm.
ultimately, it's about how our own solar system came to be.
Okay, so let's break this down a bit. I've always been kind of mind blown by just how huge everything is in space.
Mm-hmm.
We've got these giant clouds of gas and dust called molecular clouds, right?
Yeah.
They're like the stellar nurseries. I mean, it's hard to even imagine something that vast.
It is. And these clouds are cold and dark and mostly hydrogen and helium, and that's where gravity steps in. Over, well, ridiculously long periods of time, these clouds start to collapse in on themselves.
So it's kind of like a cosmic implosion.
You could say that. As the cloud collapses, it breaks up into smaller clumps, and each clump keeps shrinking, getting denser and hotter. This whole process, it can take millions of years.
Wow.
And eventually, the core of each clump gets so hot,
Yeah.
it hits a crucial temperature.
Okay, that's got to be where the magic happens, right?
It is. That intense heat and the pressure at the core, it triggers nuclear fusion. Hydrogen atoms start fusing to form helium, and that releases an unbelievable amount of energy. And that is the birth of a star.
Wow, that's incredible to think the moment a star actually ignites. And from what I've learned, that fusion is what keeps a star burning for millions, billions of years. But what happens when it runs out of fuel? I mean, do stars just sort of fade away?
Actually, they don't just disappear. They go out with a bang. They leave behind these remnants, which can be just as amazing, and in some cases even more extreme, than the stars they came from.
Remnants. So these stellar remnants, are they all the same?
Oh, no, not at all. The type of remnant a star leaves behind, it depends on its initial mass.
Oh, okay.
It's kind of like a cosmic recipe. The ingredients determine what you end up with. Now, for stars like our sun, the journey ends with a white dwarf.
Ah, white dwarfs, those tiny, super dense stellar corpses.
Exactly.
I remember reading that they're about the size of Earth, but can weigh as much as the sun.
That's right. And that extreme density, well, it's because of how matter is squeezed inside a white dwarf. Imagine cramming every single person on Earth into a subway car. That's how dense we're talking.
So it's like a cosmic mosh pit of particles.
A very energetic one. But here's the thing, even with all that density, white dwarfs don't collapse any further. They're held up by something called electron degeneracy pressure.
Okay, now that sounds complicated.
It is. It's a quantum mechanical effect that stops electrons from being in the same energy state.
Okay, so it's like these tiny particles are fighting against gravity.
You could say that. Electron degeneracy pressure, it's like internal scaffolding. It keeps the white dwarf from collapsing under its own weight.
That's incredible. And you mentioned before that white dwarfs eventually cool down and fade away, right?
They do. Over billions of years, a white dwarf will radiate its heat into space and slowly cool down. And the final stage of that cooling, that's what we call a black dwarf.
Black dwarf. So it's like a white dwarf that's gone completely dark.
Precisely. It'd be incredibly cold and hard to detect because it wouldn't give off much radiation at all.
So have we ever actually seen a black dwarf?
Not yet. The universe isn't old enough for any white dwarf to have cooled down that much, but it's a fascinating idea, a stellar remnant that's gone totally dark and silent.
It is. Okay, so we've covered white dwarfs, the end state for stars like our sun. What about stars that are much bigger? What do they leave behind?
Well, that's where things get even more extreme. We're talking about things like neutron stars and black holes.
Okay, now we're getting to the really interesting stuff. Tell me more.
Well, massive stars don't go quietly. When their core collapses, it causes a supernova, an explosion so powerful it can outshine an entire galaxy for a short time. And what's left after a supernova, well, it can be a neutron star.
Neutron stars, yeah, I remember reading. They're even denser than white dwarfs.
Imagine a star several times bigger than the sun crammed into the space of a city. That's a neutron star. The density is almost impossible to grasp.
So if a white dwarf is like squeezing everyone on Earth into a subway car, a neutron star is like squeezing them all into a thimble.
That's a pretty good way to put it. And because of that insane density, neutron stars have super strong gravity. A teaspoonful of neutron star material, it would weigh billions of tons on Earth.
Wow, that's just crazy. And are these neutron stars just, I don't know, sitting there being super dense?
Some do, but some, we call them pulsars, they spin really fast and shoot out beams of radiation, kind of like a cosmic lighthouse. When those beams sweep past Earth, we see them as pulses of radio waves.
Oh, so it's like a cosmic beacon flashing across space.
Exactly. And pulsars are amazingly precise timekeepers. Astronomers use them to study all sorts of things.
Okay, so we've got white dwarfs, black dwarfs, and these incredibly dense neutron stars. But we haven't even gotten to the most mysterious ones, black holes.
Oh yes, black holes, the ultimate cosmic enigmas.
Right.
They're so dense with such strong gravity that nothing, not even light, can escape.
That's why they're called black holes, right? They absorb all the light that falls into them.
That's it. And the boundary around a black hole where nothing can escape is called the event horizon.
Okay.
It's a point of no return, literally. Anything that crosses the event horizon, even light, is trapped forever.
So it's like a cosmic vacuum cleaner, just sucking up everything that gets too close.
Well, it's not really empty space. It's a region where gravity is so warped it's taken over.
Hold on. Warped space. That's getting pretty heavy, even for a deep dive.
Yeah, we'll dive deeper into that stuff in part 2. But for now, think of a black hole as a dent in the fabric of the universe, a place where gravity rules everything.
Okay, I think I'm starting to get it. But how do we know black holes even exist if they don't give off any light? How can we observe something that's invisible?
Great question, and it puzzled astronomers for a long time. We can't directly see black holes, but we can see how their gravity affects things around them.
Okay.
For example, if a black hole is orbiting a star, we can see how the star's motion is affected by the black hole's gravity.
So it's like seeing the footprints of a ghost. You can't see the ghost, but you know it's there.
Exactly. We can also detect black holes through the radiation given off by stuff falling into them. As matter spirals inward, it heats up and gives off X-rays and other kinds of radiation.
So even though black holes themselves are invisible, the stuff falling into them creates a kind of light show.
Exactly. And these light shows can be super energetic, and they tell us a lot about the black hole.
This is all incredible. But I have to admit, I'm feeling a bit overwhelmed. So much to learn about these things.
Don't worry, we're just scratching the surface. In the next part of our deep dive, we'll explore black holes in more detail, dig into that whole space-time concept,
Right.
and even touch on some of the other weird types of stellar remnants.
I can't wait. We'll be back soon with part 2 of our exploration of stellar evolution. Until then, keep looking up at those stars and pondering their mysteries. Welcome back to the Deep Dive, everyone, where we're journeying through the amazing life cycle of stars, from their birth to their, well, pretty mind-blowing transformations. Last time, we left off talking about black holes, those cosmic enigmas that just gobble up gravity. So are we ready to head deeper into the darkness?
You bet. Black holes are really one of the most fascinating things out there, and they really challenge what we know about physics.
For sure. So last time we talked about the event horizon, that point of no return if you get too close to a black hole. I'm still kind of struggling to imagine how something can be so dense that even light can't escape it.
Yeah, it's a tough one to grasp. It really goes against our everyday experience. Think about it this way. Imagine throwing a ball up in the air.
Okay.
Go up, slows down because of gravity, and then falls back down. Now imagine you throw it so hard it overcomes Earth's gravity and just keeps going.
Okay.
That's escape velocity, the speed you need to break free from gravity.
So is the escape velocity near a black hole just really, really high?
It's not just high, it's faster than the speed of light. And according to Einstein's theory of relativity, nothing can go faster than light, which means nothing, not even light, can get away from inside a black hole's event horizon.
So once something crosses that line, it's gone.
That's what we think. The event horizon is like a one-way door into, well, the great cosmic unknown. What happens inside a black hole is still a mystery, one that physicists are still debating and researching.
Wow. It is a bit unsettling to think there are these things out there just swallowing up whatever gets near them.
It is, but black holes aren't like cosmic vacuum cleaners roaming around sucking things up. They have gravity just like anything else with mass, but that gravity is super strong near the event horizon.
So we're safe as long as we stay away.
Exactly. And actually, black holes play a really important role in how galaxies form and change. They're probably at the center of most, maybe even all, galaxies, even ours, the Milky Way.
Oh, that's right. You mentioned Sagittarius A before, the supermassive black hole at the center of our galaxy.
Yeah.
It's millions of times heavier than the sun, right?
Yeah, that's right. And it might sound scary to have something so massive at the heart of our galaxy, but it actually helps hold everything together.
Oh, so it's like a giant cosmic anchor.
A good way to put it, supermassive black holes, they have a really strong pull on all the stars and gas clouds around them, keeping things in order.
Amazing. And you mentioned different types of black holes. What are the main ones?
We can categorize them by their mass. The most common are stellar mass black holes. They form when a single big star collapses.
So when a star way bigger than our sun dies and explodes in a supernova, it can leave behind one of these stellar mass black holes.
Right, and then you've got the supermassive black holes, like Sagittarius A. They're at the centers of galaxies.
And then there's the intermediate mass black holes.
Yeah, like the middle child, they bridge the gap between stellar mass and supermassive black holes.
Okay, so stellar mass, supermassive, and intermediate mass. Got it. Is there anything else we should know about these things?
Well, one of the most exciting discoveries lately has been gravitational waves.
Oh, right. You talked about those before. The ripples in space-time, right?
Exactly. Einstein predicted them way back when, but it took us, well, a century to develop the technology to actually detect them.
That's amazing. So how do gravitational waves help us understand black holes?
When two black holes collide, they release a huge amount of energy as gravitational waves.
So like a cosmic earthquake, sending ripples through the fabric of the universe.
I like that, a cosmic earthquake. And those ripples, we can detect them with super sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory.
LIGO, that's right. It's incredible we can basically hear these events, listen to the universe through these waves.
It's totally groundbreaking. It's opened up a whole new way of looking at the universe, and it's giving us amazing insights into black holes and the crazy environments around them.
Wow, this is all mind-blowing. I'm starting to think I need a degree in astrophysics just to understand it all.
No worries, we're taking it slow. Even the most complicated ideas can be broken down into smaller pieces.
True. So we've covered black holes, the different types, and this amazing gravitational wave science. What's next?
Let's shift gears and talk about some other interesting stellar remnants.
Okay.
Things like neutron stars, pulsars, and even dive into the hypothetical world of blue dwarfs.
Lead the way. And welcome back to the deep dive. We're on the last part of our exploration into the fascinating world of stellar evolution. We've gone from the birth of stars in those massive molecular clouds all the way to the, well, crazy physics of black holes. You know, those cosmic traps that even light can't escape.
It's been quite a journey. We've encountered some pretty wild objects along the way.
It has. We've talked about white dwarfs, those stellar embers that are literally being held up by the, well, defiance of their own electrons. And we even peeked into the theoretical future with those black dwarfs, the final whispers of what were once these brilliant stars.
And of course, we can't forget about neutron stars, those city-sized spheres packed with more mass than our sun.
Right, they're like the ultimate cosmic heavyweights. Their gravity is so strong it makes Earth's pull seem like nothing.
And what's fascinating is that neutron stars aren't just incredibly dense, they're also dynamic. Some, the ones we call pulsars, spin incredibly fast, emitting beams of radiation. It's like they're cosmic lighthouses sweeping across the galaxy.
It's amazing to think that something so chaotic, born from a supernova, can be so regular and precise.
It really shows the power of the forces at play in the universe. Even in the aftermath of a star's death, there's this kind of order that emerges. And pulsars aren't the only type of neutron star that keeps things interesting.
Oh, that's right. We also touched on magnetars, those neutron stars with magnetic fields so strong they can actually distort atoms.
Exactly. It's as if they're playing with the very building blocks of matter. Magnetars are still quite mysterious, but they're another example of the extreme conditions that stellar evolution can create.
Absolutely. And speaking of extremes, we can't forget about those theoretical blue dwarfs.
Right, the stars that might evolve from the incredibly long-lived red dwarfs. It's a fascinating possibility. The most common type of star in the universe might actually have a second act, becoming even hotter and brighter.
It highlights the vastness of time involved in stellar evolution.
Hmm.
Our sun lives for billions of years, but red dwarfs burn for trillions, giving them plenty of time to maybe transform into blue dwarfs.
It's like the universe is unfolding in slow motion, with some stars taking their time to reach their full potential.
That's a great way to put it. So when we think about the whole process, From those initial clouds of gas and dust to the remnants like white dwarfs, neutron stars, and black holes, it's clear that stellar evolution is this grand cosmic ballet.
It is a ballet of creation and destruction where stars are born, live out their brilliant lives, and then leave behind these incredible objects that continue to shape the universe. And by studying these remnants, we're not just learning about individual stars, we're learning about the fundamental laws of physics, the origins of the elements, and our place in the cosmos.
It really is humbling to think that the elements that make up our bodies, our planet, everything around us, were forged in the hearts of stars that lived and died long ago.
It's a connection that shows how everything in the universe is interconnected. We are quite literally stardust.
That's a beautiful way to think about it. And with that thought, we've reached the end of our deep dive into stellar evolution. I hope you've enjoyed the journey as much as I have. It's been an incredible exploration of the life cycle of stars, from their fiery beginnings to their, well, sometimes bizarre afterlives.
I've certainly enjoyed sharing this cosmic adventure.
And to all of our listeners, thank you for joining us on the deep dive. We hope you've gained a new understanding of the wonders of the universe and the amazing stories that stars have to tell. Don't forget to like, subscribe, and hit that notification bell so you don't miss our future explorations into the realms of science and knowledge. Until next time, keep looking up at the stars and keep wondering.